Good day. This is MEG 224, Engineering Mechanics 2, Dynamics. Lecture 8, Planar Kinetics of Rigid Body, the Principles of Work and Energy, Part B. This can be found in Chapter 18 of Engineering Mechanics, Dynamics by R.C. Hibella. This Part B is a continuation of Part A. Lecture objectives for Part B. The objectives of this lecture are to apply the principle of work and energy to solve rigid body planar kinetic problems that involve force, velocity, and displacement. Then, to show how the conservation of energy can be used to solve rigid body planar kinetic problems. Principle of work and energy. By applying the principle of work and energy developed earlier to each of the particles of a rigid body and adding the results algebraically, since energy is a scalar, the principle of work and energy for a rigid body becomes T1 plus summation U1 to 2 is equal to T2. This equation states that the body's initial translational and rotational kinetic energies plus the work done by all the external forces and couple moments acting on the body as the body moves from its initial to its final position is equal to the body's final translational and rotational kinetic energies. Note that the work of the body's internal forces do not have to be considered. These forces occur in equal but opposite collinear pairs, so that when the body moves, the work of one force cancels that of its counterpart. Furthermore, since the body is rigid, no relative movement between these forces occur, so that no internal work is done. When several rigid bodies are pinned together or connected by inextensible cables or in a mesh with one another, the above equation can be applied to the entire system of connected bodies. In all these cases, the internal forces which hold the various members together do no work and hence are eliminated from the analysis. Conservation of energy. When a force system acting on a rigid body consists of only conservative forces, the conservation of energy theorem can be used to solve a problem that otherwise would be solved using principle of work and energy. This theorem is often easier to apply since the work of conservation or conservative force is independent of the parts and depends only on the initial and the final position of the body. It was shown earlier that the work of conservative force can be expressed as the difference in the body's potential energy measured from an arbitrarily selected reference or datum, gravitational potential energy. Since the total weight of a body can be considered concentrated at the center of gravity, the gravitational potential energy of the body is determined by knowing the height of the body's center of mass or center of gravity above or below a horizontal datum. So this is the horizontal datum. This is the body above the horizontal datum and the body below the horizontal datum. So here, Vg is Wyg. Here, the potential energy is positive when Yg is upward. Is positive upward. Since the weight has the ability to do positive work when the body moves back to the datum as shown in the figure. Likewise, if G is located below the datum, that is minus Yg, the gravitational potential energy is negative since the weight does negative work when the body returns to the datum. Elastic potential energy. The force developed by an elastic spring is also a conservative force. The elastic potential energy, which a spring imparts to an attached body when the spring is stretched or compressed from an initial undeformed position S is equal to 0 to a final position S in the figure is VE, that is the elastic potential energy, is half ks squared. In the deformed position, the spring force acting on the body always has the ability to do positive work when the spring returns back to its original undeformed position. Here, when you compress a spring and you put a load on it, it will push the load to return to its original stretch position. In that case, the work is positive because displacement and force are in the same direction. Conservation of energy. In general, if a body is subjected to both gravitational and elastic forces, the total potential energy can be expressed as a potential function represented as the algebraic sum. V is equal to Vg plus Ve. That is, the total potential energy is equal to the gravitational potential energy plus elastic potential energy. Here, measurement of V depends on the location of the body with respect to the selected datum. Realizing that the work of conservative forces can be written as a difference in their potential energies, V1 minus V2, we can rewrite the principle of work and energy for a rigid body as T1 plus V1 plus summation of U1 to 2 for non-conservative forces is equal to T2 plus V2. Here, the summation of U from 1 to 2, from position 1 to 2 non-conservative force represents the work of the non-conservative forces, such as friction. If this term is 0, then T1 plus V1 is equal to T2 plus V2. This equation is referred to as the conservation of mechanical energy. It states that the sum of the potential energy and kinetic energies of the body remains constant when the body moves from one position to another. It also applies to a system of smooth pin-connected rigid bodies, bodies connected by inextensible cords, and bodies in mesh with other bodies. In all these cases, the forces acting at the point of contact are eliminated from the analysis, since they occur in equal but opposite collinear pairs, and each pair of forces move through an equal distance when the system undergoes a displacement. It is important to remember that only problems involving conservative force systems can be solved by using this equation. As stated earlier, friction and other drag-resistant forces, which depend on velocity and acceleration, are non-conservative. The work of such forces is transformed into thermal energy used to heat up the surfaces of contact, and consequently, this energy is dissipated into the surroundings and may not be recovered. Therefore, problems involving frictional forces can be solved by using either the principle of work and energy written in this form, if it applies, or the equation of motion. So now let's look at example, or let's look at a tutorial for this lecture 8. So the bar shown in figure A has a mass of 10 kilograms and is subjected to a couple moment of M is equal to 50 Newton meter, and force of P equals to 80 newtons, which is always applied perpendicular to the end of the bar. He said also the spring has an unstretched length of 0.05 meters. This is the spring, and remains in the vertical position due to the roller guide at B. Determine the work done by all the forces acting on the bar when it has rotated downward from theta is equal to 0 to theta is equal to 90 degrees. Solution. We first of all draw the free body diagram of the bar to account for all the forces that act on it, as shown in figure B. At this point, we have the reaction at the pin AY and AX. Then Fs is the spring force. This should be weight. Then this is the couple moment, and this is force P. Weight. Since the weight is 10 kg times 9.81 meters per second, so then it's 98.1, and it's displaced downward. Because the weight of this body will act at the middle of the bar, and the bar is 3 meters long. So the weight is acting at the bar here. So, and it has traveled downwards because we're not looking at the path that the weight is taking. We are only looking at the differential of the initial position of the weight and then the final position of the weight. The initial position of the weight is when theta is equal to 0, and then the final position is when theta is equal to 90 degrees. And from that place, from this position, so horizontal position to vertical position, the weight has moved by 1.5 meters. So the work done is force times distance, which is 9.81 times 1.5, which is 147.2 joules. Why is the work positive? The work is positive because the direction of the weight and the direction of displacement, they are the same. So force and displacement, they are in the same direction. Couple moment. The couple moment rotates through an angle of theta is equal to pi over 2 radian. Hence, from our formulation, m is theta 2 minus theta, m into theta 2 minus theta 1. Theta 1, which is the initial position, is equal to 0. So the work done by the moment is m theta 2, which is 50 times pi over 2, which is 78.5 joules. Then the spring force. The spring has an undeformed length of 0.5 meters. But the initial position when theta is equal to 0 is 0.75. Therefore, the spring has stretched by 0.25 in addition to its original length of 0.5, which makes it 0.75. So the spring at theta 0 has stretched 0.25 meters. And so theta, when theta is equal to 90 degrees, the stretch is 2 meters plus 0.25, because here 0.75, we now take the unstretched position from it because the spring is hinged at 2 meters from the hinge. So, which is 2.25. Therefore, the work of the spring is half ks s2 square minus s1 square. That is the final position minus the initial position, which gives us this, and then which is minus 75.0. So the spring does negative work on the bar since Fs acts in the opposite direction to displacement. The spring is pulling back the bar while the bar is being pushed down. So the spring pulls it back. So that's why it's doing displacement, and the force of the spring is upward while displacement is downward. So they are in opposite directions. So force P, as the bar moves downward, the force is displaced through a distance of pi over 2 times 3 meters. So the force moves through that, which is 4.712. So the work done by this force is 80 times 4.712, which is 377 joules. So this work, the work is positive because the displacement, the direction of the force and the displacement, they have the same sense. So pin reactions. The reactions as a pin is AX and AY. But since this, at this pin, there is no displacement, then our work is force times displacement. When displacement is 0, then the work done is 0. So forces AX and AY do no work since they are not displaced. There's no displacement. So the total work done. So the total work done by all the forces. When the bar is displaced, it does all this together, which is 528 joules. Thank you. End of part B. So do not forget to like my videos, to subscribe to my video channel, to share my videos, and press the notification bell for new videos. If you are one of my university undergraduate students, please do not forget to subscribe with your real name. Thank you, and God bless you. I will meet you in the next video.